Welcome to InfoSec Bytes, your go-to podcast for bite-sized insights on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis. With over 100 episodes, we've got you covered on the latest trends and tips. This year, we will focus more on cloud computing along with other topics, so stay tuned. Please like, subscribe, and share to join the conversation on various platforms: Spotify, Apple Podcasts, YouTube, Amazon Music, and stay secure.
Absolutely.
And we have a massive, highly technical agenda ahead of us today. We are taking a deep dive into a really towering stack of research covering the intricate realities of cross-cloud security models.
Yeah, it's a lot.
It is. We're breaking down the architectural differences across AWS, Azure, GCP, and OCI. We are going to tear into the Cloud Data Lifecycle Management architecture. We will be navigating the labyrinth of global regulatory compliance, looking at the new NIST frameworks, ISO 27017, GDPR, and HIPAA.
Right.
And we're going to untangle the highly complex world of encryption key management, specifically diving into the architectural trade-offs between BIP and HYO architectures.
It's an incredibly dense stack of research. And before we get into the technical weeds, I want to just acknowledge who we are really talking to today.
Yeah, let's do that.
Because if you are listening to this, you are likely a cloud architect, a GRC analyst, an auditor, or a security engineer. And we know exactly what your daily reality looks like.
It's stressful.
It is. You are caught in this relentless tug of war. On one side, your engineering teams are pushing for rapid, agile deployments. They are utilizing infrastructure as code to spin up resources across multiple clouds at breakneck speed. They want frictionless pipelines.
And on the other side?
On the other side, you are staring down strict data sovereignty laws, highly complex compliance frameworks, and the ever-present threat of a crippling audit failure.
Yeah.
Audit fatigue isn't just a concept for you. I mean, it is a daily operational reality. Multi-cloud complexity means you are translating policies across entirely different operational paradigms.
Yeah.
You are expected to be the gatekeeper, the enforcer, and the enabler all at once. So this deep dive is built specifically to help you navigate that exact architectural tension, looking at the actual technical controls that satisfy these seemingly impossible legal requirements.
Absolutely. And that tension is where architectures either scale beautifully or they just completely break down under audit scrutiny. So rather than just listing off frameworks from the research, we want to trace the actual journey of a piece of data through a multi-cloud environment.
I like that approach.
Right. Examining the security controls, the IAM policies, and the cryptography required at every single step. So let's start by looking at the Cloud Data Lifecycle Management, or CDLM, architecture.
Let's do it.
The research we are reviewing makes it abundantly clear that CDLM is a highly dynamic multi-stage cycle. Managing each of these stages properly dictates your operational costs, your security posture, and your compliance status.
It really is the foundation.
But I want to address the elephant in the room first.
Right.
Data sprawl. For the GRC analysts and architects listening, let's just drop a quick host note on how we are defining this technically today.
Yeah, that's important.
Data sprawl isn't just about messy S3 buckets. We are talking about the unmanaged, rapid proliferation of data across multiple cloud instances, orphan EBS volumes, disconnected RDS snapshots, shadow IT environments.
The stuff that keeps you awake at night.
Exactly. It's when a developer copies a production database to a lower environment for testing and just entirely forgets to scrub the PII. That sprawl leads directly to massive compliance violations because you simply cannot secure what you cannot see.
Precisely. Data sprawl is the absolute enemy of governance. I mean, if you don't know where the data is, you cannot map it to a compliance framework.
Right.
And you certainly cannot prove to an auditor that you are meeting your regulatory obligations.
Yeah.
This is why a rigorous programmatic approach to the CDLM phases is so critical. It forces an organization to architect a life cycle for every single byte of data.
So looking at that initial entry point, creation and acquisition, this is where data actually enters your ecosystem.
Right, ingress.
We are talking about API gateways ingesting third-party payloads, Kafka streams processing IoT telemetry, or direct user input. The research leans heavily into the concept of privacy by design at this exact ingress point.
It does.
But I see the premise of privacy by design, but how does an architect actually enforce that at the point of ingestion without completely throttling the engineering teams? We can't manually inspect every JSON payload hitting an API gateway.
No, you can't. You enforce it through programmatic data minimization and automated classification. First, from an application architecture standpoint, you only design endpoints to accept the data strictly necessary for the business function.
Okay, give me an example.
If the microservice doesn't need a user's precise geolocation to process a transaction, the API should strip that payload out before it ever hits the message queue.
Just drop it entirely.
Dropped entirely. But more importantly, you need automated classification tagging the millisecond that data is written to storage. Tools like Amazon Macie or Microsoft Purview should be configured to automatically scan incoming objects.
Using pattern matching, right?
Exactly. Pattern matching and machine learning to identify data types. Is this a 9-digit number formatted like a social security number? Tag it as highly sensitive PII. Is it a health record? Tag it as PHI. If you don't apply these metadata tags at creation, the data immediately becomes part of that unmanageable sprawl.
And that tagging taxonomy is what drives the automation for the rest of the lifecycle.
Yes.
Once we've classified the data at ingestion, the immediate next headache for the architect is storage and maintenance. This is where we are committing that data to AWS S3, Azure Blob Storage, or Google Cloud Storage.
It's static-based mostly.
Right. From an infrastructure perspective, the research emphasizes automated storage tiering. If we are tagging data correctly, we can write lifecycle rules that say if this object is a standard access log, keep it in standard S3 for 30 days, then automatically transition it to S3 Glacier Deep Archive.
Which saves massive amounts of capital.
It does, but from a resilience and security standpoint, we really have to talk about the 3-2-1 backup rule in a cloud-native context.
Right. The 3-2-1 rule is foundational. 3 total copies of your data on 2 different media types with 1 copy off-site. In a cloud architecture, off-site translates to geographic and logical isolation.
Meaning you don't just back up to the same account.
Exactly. You don't just back up your primary database to an S3 bucket in the same AWS account in the same region. If an attacker compromises your IAM credentials, they will encrypt your primary data and your backups simultaneously.
Game over.
Complete game over. You need cross-region replication to an entirely separate, isolated AWS account, a vault account where your primary IAM roles have absolutely zero access. This cross-account, cross-region architecture protects you against regional outages, but more importantly, it creates an air gap against ransomware lateral movement.
I want to push back slightly on that, though, for the folks dealing with the budget. Cross-region replication sounds great for an audit, but data egress costs between cloud regions can be absolutely exorbitant.
But they are.
If you are moving petabytes of telemetry data to a vault account in a different geographic region, the CFO is going to be knocking on your door very quickly.
And that is the exact tension we talked about at the beginning. Security versus cost.
Yeah.
You're absolutely right about the egress costs. This is why that initial classification phase is so critical.
Tying it back to the tags.
Yes. You do not replicate your easily replaceable marketing assets or transient cache data across regions. You apply that strict multi-region 3-2-1 architecture only to your mission-critical databases and compliance-bound records. You use the metadata tags to drive the routing logic, ensuring you are only paying the premium resilience costs for the data that actually warrants it.
That is a critical distinction. Tagging drives cost efficiency as much as it drives security. Now, moving into the active kinetic state of the data, the usage and processing phase.
This is where it gets dangerous.
It is. Data isn't just sitting in an encrypted bucket anymore, it is being queried. We are running Spark jobs on EMR clusters, we are querying Snowflake data warehouses, and critically, we are training AI models.
Yet AI adds a whole new layer of risk.
Looking at the research, the risk vector that screams out to me here is shadow AI. Developers are incredibly eager to leverage large language models. They will point an LLM ingestion pipeline at a massive internal data lake to build a retrieval augmented generation, or RAG, system.
And if they aren't careful?
Right. If they accidentally ingest untagged PII, they have effectively baked that sensitive data into the vector database, or worse, into the model's parameters itself.
That is a massive emerging threat surface. Once PII is ingested into an AI model's training data, extracting it is nearly impossible without entirely retraining the model from scratch.
Which costs a fortune in compute.
A literal fortune. This is why your extract, transform, load your ETL and ELT pipelines must act as rigorous security checkpoints. As data is pulled from storage for processing, you must enforce dynamic data masking and anonymization at the driver level or the data's proxy level.
Can you break down the mechanics of dynamic data masking for the listeners architecting these pipelines? How do we give a data scientist what they need without exposing the raw payload?
Let's take a practical scenario. You have a data scientist building a machine learning model to detect credit card fraud. To train that model, They need to analyze purchasing behaviors, transaction amounts, and geographic trends.
But they don't need the card numbers.
Exactly. They do not need to see the actual plain text 16-digit credit card number. In a dynamically masked architecture, you use role-based access control integrated with your processing engine. When the data scientist queries the database, the system recognizes their IAM role.
And intercepts the request.
On the fly. In memory, the system replaces the credit card number with a mathematically consistent token, or it masks all but the last 4 digits. The data scientist receives the dataset they need to build a behavioral model, but the raw PII never actually touches their compute instance.
That's brilliant.
You are enforcing the principle of least privilege at the data layer, not just the infrastructure layer.
That is a phenomenal architectural pattern. You govern the access to the data's utility, not just access to the file itself. Which brings us to the sharing and transfer phase.
Moving data around.
Yeah, this involves moving data between internal business units or exposing it to third-party vendors. The traditional method was to run an export, generate a CSV, encrypt it, and drop it on an SFTP server.
Please don't do that.
Right, but that just creates more data sprawl and duplicate environments. The research points heavily toward federated access models.
Exactly. Duplicating a dataset for a vendor is an antiquated, high-risk approach. Once you copy that data and hand it over, you've lost all technical governance over it. You're relying entirely on the vendor's honor system to delete it when they are done.
Which auditor is going to accept an honor system?
None of them. Modern architectures utilize cross-account roles and secure API integrations. In AWS, this would be an STS assume role. In Azure, you might use Azure Lighthouse. Instead of giving the vendor the data, you give the vendor's application a tightly scoped, temporary, federated IAM role.
So they come to you.
Yes. This role allows their application to query your data where it natively resides, perhaps through a secure API gateway. You maintain the single source of truth, you can revoke the access instantly with a single API call, and every single query they make is logged in your CloudTrail or Azure Monitor for auditing purposes.
You govern the access, you don't duplicate the data, and that continuous auditing leads perfectly into the archival and preservation phase.
Legal hold phase.
Yeah, this isn't usually an architectural choice, it's a legal mandate. If you are in the financial sector, you are dealing with SEC Rule 17A4. If you are a publicly traded company, you are dealing with SOX compliance.
Highly rigid requirements.
For the GRC analysts tracking this, let's establish another host note here regarding WORM compliance. WORM stands for write once, read many. The research makes it clear that immutable storage architectures are non-negotiable for regulated industries.
Absolutely non-negotiable.
But how does an architect actually prove immutability in a cloud environment where an administrator with root access theoretically has the power to delete anything?
Proving immutability in the cloud requires leveraging specific hardware-backed provider controls. You cannot just use a standard file system permission that says read-only because, as you mentioned, a root user can just change that permission.
Right, it's too flimsy.
You have to use features like AWS S3 Object Log, specifically deployed in compliance mode. When you put an object in an S3 bucket with Object Lock compliance mode, enabled for a retention period of, say, 7 years, that object is mathematically and operationally locked.
Even from root?
Even if a malicious actor compromises the root credentials of the entire AWS account, they cannot modify or delete that object. Even AWS support engineers cannot delete that object. It is protected at the control plane level until that time lock expires. That is what auditors require when you say your records are worm compliant.
Which makes the final phase, destruction and purging, incredibly complex. If the data is locked or if it is scattered across snapshots, standard file deletion is useless.
Oh, standard deletion is a myth in the cloud.
I want to look at the reality of data destruction in a multi-tenant cloud for a second. If you are running an on-premise data center and a hard drive reaches the end of its life cycle, you pull it out of the rack, you put it in a literal industrial fretter, and you issue a certificate of destruction.
The old school way.
You obviously cannot do that in a Google or Microsoft data center. You don't own the disk. So how do you verify destruction to an auditor?
This is one of the most difficult concepts for traditional auditors to grasp. In the cloud, the physical media is entirely abstracted away from you. A single hard drive in an Azure data center might contain fragments of your database alongside fragments of 10 other companies' databases.
You can't shred the drive.
You cannot physically destroy the drive. Furthermore, you have the massive risk of zombie data fragments of your environment that survive in automated backups, EBS snapshots, or decoupled storage volumes that you simply forgot existed.
Sprawl comes back to haunt you.
Exactly. This is why the only acceptable standard in the cloud is cryptographic erasure, often called crypto shredding.
And the architecture of crypto shredding requires you to plan for destruction at the exact moment of creation, right? You have to be using envelope encryption from day one.
You nailed it. You encrypt the data using a data encryption key, a DEEK. That DEEK is then encrypted by a master key encryption key, a key managed in your key management service.
Okay, so you have this nested Russian doll of encryption.
Right. When the time comes to purge the data, whether it is a user requesting the right to be forgotten under GDPR or a legal hold expiring, you don't try to track down every single fragment of that data across all your snapshots to overwrite the physical sectors.
That'd be impossible.
Instead, you permanently delete the master key encryption key in your KMS.
Just delete the key.
The moment that key is deleted, the data, all its backups, and all its scattered snapshots instantly become mathematically inaccessible ciphertext. It is permanently cryptographically shredded. For your auditor, the verifiable certificate of destruction is the immutable log entry in CloudTrail, or your SIEM, proving that the specific KMS key was permanently deleted.
That is a phenomenal breakdown of the lifecycle. You destroy the math required to read the data, rather than trying to destroy the abstracted hardware.
It's the only way that scales.
Now let's pivot to the core engine that enforces all of this. We need to do a deep dive into identity and access management and the shared responsibility model across the different cloud providers.
The IAM showdown.
Yeah. We hear the phrase shared responsibility model so often it has almost lost its meaning. But for the architect on the ground, the line between what the cloud service provider owns and what the customer owns is often incredibly blurry, especially as we move up the stack from infrastructure as a service to platform as a service.
It is the most critical line of demarcation in cloud security. The baseline understanding is that the CSP secures the infrastructure of the cloud, the concrete facilities, the biometric locks, the hypervisor patching.
Physical stuff.
Right. You, the customer, secure everything in the cloud, your data, your application code, and your IAM configurations. But you were right, it gets blurry fast.
Walk us through that blurriness.
If you spin up a raw EC2 virtual machine, you are responsible for patching the guest operating system, updating the libraries, and managing the firewall. But if you use a managed service like Amazon RDS for your database, AWS takes over the operating system patching and the database engine updates.
But you aren't off the hook.
No. You still own the IAM policies dictating who can access that RDS instance, and you still own the configuration flag that determines whether that database is publicly exposed to the internet.
Which is where the breaches happen.
The vast majority of cloud breaches are not zero-day exploits against the hypervisor. They are customers failing their portion of the shared responsibility model by leaving an S3 bucket, public or hard-coding IAM access keys in a GitHub repository.
And because the customer owns IAM, we really need to look at how the major providers handle identity and policy because they architect it very differently. The research provides an excellent cross-cloud showdown here. Let's start with the undisputed heavyweight, AWS. How would you characterize their IAM architecture from an engineering perspective?
AWS IAM is exceptionally granular, multi-layered, and extraordinarily powerful. But that power introduces a massive operational complexity.
Yeah, the JSON policies.
Exactly. In AWS, policies are written in JSON format. You are explicitly defining the principle, the action, the resource, and the condition. You can write a policy that says, this specific IAM role can perform the s3.get object action only on this specific bucket, only if the request originates from this specific VPC endpoint, and only between 9 a.m. and 5 p.m.
It's incredibly precise.
It is. But because you can get that granular, misconfigurations are incredibly easy to introduce and very difficult to audit manually.
Let me give a scenario to highlight that risk for the audience. Let's say a developer creates a role for an EC2 instance to read an S3 bucket, but they use a wildcard and asterisk in the resource block, and they don't set a condition key restricting the network origin.
That is a classic privilege escalation vector. By using that wildcard, the developer hasn't just given the EC2 instance access to the intended bucket, they have given it permission to read every bucket in the account. Yeah, if an attacker compromises that single EC2 instance, they inherit those overly permissive IAM credentials, and they can exfiltrate your entire data lake.
So how do you stop that at scale?
This is why managing AWS at an enterprise scale requires heavy governance tools. The research points to AWS Control Tower and the use of service control policies, or SCPs.
Oh, the CPs are the big hammers.
They are the ultimate guardrails.
Rope.
SCPs are applied at the organizational level, An SCP can dictate that no matter what permissions a developer grants an IAM role, no one in the entire organization is allowed to disable CloudTrail logging or deploy resources outside of the U.S. East 1 region. It is a preventative, heavy-handed control necessary to tame the complexity of individual JSON policies.
That preventative approach is vital. You have to build the bumper bowling lanes before you let the developers throw the ball.
Great analogy.
Now, how does Microsoft Azure approach this? The research describes their model as much more enterprise-ready and familiar to traditional IT shops.
Azure approaches cloud identity heavily through the lens of traditional on-premise enterprise architecture. Their model utilizes a dual system, role-based access control, or RBAC, and Azure policy. And the identity backbone is Entra ID, what used to be Azure AD.
So what's the architectural advantage there?
What is particularly elegant about the Azure architecture is the strict separation between access and compliance. RBAC handles the who and the what. It defines that a specific security group has the contributor role over a specific resource group.
Okay, so that's the access part.
Right, but Azure policy handles the how. Azure policy evaluates the configuration state of the resources being deployed.
So, practically speaking, how does an auditor leverage that separation of duties?
It allows the auditor to enforce compliance without breaking developer workflows. A developer might have the RBAC permissions to deploy a virtual machine, but the GRC team can implement an Azure policy that states all virtual machines must have encryption at rest enabled and must be deployed in the West Europe region.
And if the developer ignores that?
When the developer attempts to deploy a VM without encryption via an ARM template or Terraform, the Azure Resource Manager evaluates it against the Azure policy and simply denies the deployment before the infrastructure is ever provisioned.
It stops it cold.
It stops the misconfiguration at the control plane level. This deep integration with tools like Defender for Cloud provides a unified, policy-driven posture management system that feels very intuitive to teams that grew up managing Active Directory group policy objects.
I see the appeal there. It centralizes the compliance rules away from the individual user roles. Let's look at Google Cloud Platform, GCP. The research describes their IAM model as hierarchical and additive. For an architect migrating from AWS to GCP, this additive nature is often a massive stumbling block. How does it function?
It is a completely different paradigm. GCP uses a strict resource hierarchy. You have an organization at the root, which contains folders, which contain projects, which contain resources.
A very clean tree structure.
Yes. IAM policies in GCP cascade downwards. The additive nature means that if you grant a user the storage object admin role at the folder level, they inherit that full administrative capability for every single project and every single bucket within that folder.
Okay, but what if I want to block them from one specific project?
You can't. Crucially, you cannot use a lower-level policy to explicitly deny a permission that was granted at a higher level. If the organization level says they have access, a project-level policy cannot revoke it.
That sounds like a nightmare for enforcing least privilege if you aren't careful. How do you draw a security boundary in GCP if permissions just relentlessly cascade down?
You utilize two mechanisms. First, organization policy constraints, which are similar to AWS SCPs. They act as high-level Boolean rules. You can set a constraint that says, disable API access to external IPs for an entire folder.
Okay, that helps. And the second?
The real power in GCP, which the research heavily highlights, is VPC service controls. This is how you draw a hard logical perimeter around your GCP resources. You can define a perimeter around a specific project.
Like a moat?
Exactly like a moat. Even if a user has the IAM permissions to access a BigQuery dataset within that project, if their API request originates from outside the designated VPC or from an untrusted device, the VPC service control blocks the request.
It looks at the context.
It relies on context-aware access.
Yeah.
Evaluating the network origin, the device posture, and the identity simultaneously. It is a highly sophisticated, zero-trust architecture built natively into the platform.
That context-aware access is really where the industry is heading. Identity is no longer just a username and password. It is the context of the request itself.
Absolutely.
Finally, let's touch briefly on Oracle Cloud Infrastructure, OCI. They cater to a very specific, highly regulated enterprise market. What is their architectural differentiator?
OCI is obsessively focused on strict logical isolation. They utilize a construct called compartments to organize resources, but they go a step further with security zones and realms.
Realm.
Yeah. A realm allows an organization to create a boundary where even OCI cloud administrators, the actual Oracle employees, cannot access the customer's data or resources. Furthermore, OCI emphasizes full-service parity across their public, dedicated, and sovereign cloud deployments.
Meaning you can run the exact same stack anywhere.
Precisely. If you build an architecture utilizing their maximum security baselines in the public cloud, you can lift and shift that exact architecture to a disconnected, air-gapped sovereign region without losing any security tooling or compliance posture. It is purpose-built for government and critical infrastructure workloads.
Okay, we have covered the CDLM lifecycle, and we have dissected the IAM architectures controlling access to that data. Now we arrive at the absolute cryptographic core of this entire deep dive.
This is the big one.
It is. We need to unpack the encryption key management dilemma. Here is the undeniable reality for every GRC analyst listening. Encryption defaults do not matter if you do not control the keys.
Say it louder for the people in the back.
Right. If your data is encrypted at rest, but a third party holds the master key, your data is only as secure as their internal policies and their susceptibility to legal subpoenas.
Exactly.
The research provides a phenomenal breakdown of the three primary architectures for key management. Let's do a rigorous technical exploration of each, starting with provider-managed keys.
Provider-managed keys are the default baseline for cloud computing. When you spin up an S3 bucket or an Azure Blob container, the data is encrypted at rest using AES 256 transparently.
It's automatic.
Completely.
Yep.
The cloud provider generates the master key, stores it in their internal infrastructure, and automatically rotates it. It is entirely frictionless. The developer does absolutely nothing, and the compliance team gets to check a box saying data is encrypted at rest.
But let's look at the architectural reality underneath that checkbox. Because the CSP generated that key and holds it in their own operational memory, they possess the technical capability to decrypt your data.
They do.
Now, I'm not suggesting AWS engineers are snooping through your databases for fun. The risk isn't malicious employees. The risk is legal compulsion. If the provider is served with a government subpoena or a national security letter, they can decrypt your data and hand it over without your consent, and often without even notifying you due to gag orders.
Exactly right. For a highly regulated organization dealing with sensitive intellectual property or foreign citizen data, provider-managed keys represent an unacceptable loss of cryptographic sovereignty. You have outsourced the ultimate control of your data.
Which naturally leads organizations to the second model, which is heavily marketed by the cloud providers, BYO, or bring your own key.
Ah, BIO.
Yeah, I've always found BYO to be a bit of a shell game. The analogy I use to explain it to my audience is that BYO is like buying your own high-end, unpickable deadbolt, installing it on the door of your rented apartment, but then handing the master key over to the landlord. You own the lock, but the landlord can still walk in whenever they want.
That is the perfect analogy.
Let's break down the technical workflow of BYK to understand why that analogy holds up. How does the architecture actually function?
In a BYOC architecture, you do not let the cloud provider generate the key material. Instead, you generate the master key material on premises, usually inside your own highly secure hardware security module and HSM. This guarantees the cryptographic entropy and the origin of the key.
So you control the genesis of the key.
Yes. You then take that key material, wrap it securely, and upload it via TLS API calls to the cloud provider's managed service AWS KMS or Azure Key Vault.
Okay, so the key is now sitting in the cloud provider's KMS. When an application needs to read a file, what actually happens?
This is where the vulnerability lies. When your application requests a file, the provider's infrastructure performs the cryptographic operation. The provider's KMS loads your key material into its operational memory to decrypt the data encryption key, which then decrypts the file.
Wait, so the key is in memory?
Yes. The critical flaw is that while the key is actively being used for that cryptographic operation, it exists in plain text in the CSP's memory enclave. Yes, you have control over the key's lifecycle. You can log when it is used, you can rotate it on your own schedule, and you can revoke it, instantly breaking access to the data.
Out for a bet.
But the undeniable technical reality is that the provider still possesses the key material. If they are served with a subpoena, they can take that key material from their KMS and decrypt your data. BU gives you lifecycle control, but it does not give you absolute data privacy. It is, in many ways, security theater for compliance frameworks that don't look deep enough into the architecture.
And that realization is causing massive panic among European architects and GRC analysts right now. If BIT still leaves the key in the provider's hands, the only technical solution for absolute, undeniable data privacy is the third model. HYOK, hold your own key, which is also referred to as CSEK, customer-supplied encryption keys.
HYOK is the absolute paradigm of cryptographic control. In this architecture, the master encryption keys never leave your customer-controlled on-premises hardware or your isolated private cloud. They're never uploaded to AWS KMS or Azure Key Vault.
So if the keys never leave your on-premise data center, how does a cloud application sitting in AWS actually encrypt or decrypt anything? Walk us through that network flow.
It requires a highly complex hybrid architecture. Let's say a cloud application needs to decrypt a payload. The application sends the encrypted payload or the request for a cryptographic operation across the network over a dedicated express route or direct connect back to your on-premises data center.
All the way back home.
All the way back. Your on-premise Thales, or Luna HSM, receives the request, performs the mathematical decryption locally within its secure boundary, and sends the plaintext back across the network to the cloud application.
Meaning the cloud provider never sees the math.
Exactly. The cloud provider has zero technical ability to decrypt the data at rest because they literally never possess the key material at any point in time. Even if they are subpoenaed, they can only hand over mathematically useless ciphertext. The research mentions platforms like Kiteworks utilizing private deployments to enforce strict HYOK architectures, guaranteeing that even the platform vendor cannot access the customer's communications.
HYOK gives you absolute cryptographic sovereignty. But let's play devil's advocate here, because the operational trade-offs for the architecture team are just staggering. This is not a frictionless deployment.
Not at all.
First, you are introducing massive network latency. Every single time a cloud application needs to read a file, it has to make a network round trip back to your on-premise data center. If you're processing millions of transactions a second, that 50-millisecond round-trip latency will completely bottleneck your application's performance.
Latency is a massive hurdle, but the availability risk is even more terrifying. In a HYOK model, you are entirely responsible for maintaining a highly available fault-tolerant key management infrastructure on-premises.
If the network goes down.
If your on-prem network goes down, or your HSM cluster fails, your entire cloud environment effectively goes dark. Your cloud applications cannot decrypt anything.
That's a huge single point of failure.
And the ultimate nightmare scenario, if your data center burns down and you lose the master key material because you didn't have adequate offline backups, your entire multi-petabyte cloud data lake is cryptographically shredded forever. Yeah. There is no forgot password link you can click with AWS. The data is gone. The operational burden of managing HYOK is immense.
It is a terrifying level of responsibility. But here is why highly regulated industries are willing to take on that operational nightmare. We have to discuss the U.S. Cloud Act double bind. This is the geopolitical headache that is keeping European GRC analysts awake at night.
It's a massive legal conflict.
Let's unpack the legal paradox here. The U.S. Cloud Act is a piece of legislation that essentially grants United States law enforcement extraterritorial reach. It allows the U.S. government to compel American cloud service providers like AWS, Microsoft, and Google to produce data stored on their servers, regardless of where in the world those servers are physically located.
Exactly.
So if you are a German company and you intentionally deploy your architecture exclusively in the AWS Frankfurt region to satisfy German data residency requirements, the U.S. government can still serve a Cloud Act warrant to AWS in Seattle, forcing them to produce your data.
And this creates an unresolvable jurisdictional conflict. If you are a European company, you are bound by the GDPR, which strictly regulates how personal data can be accessed and mandates protection against unauthorized third-country surveillance.
So you're stuck in the middle.
You are. If you use provider-managed keys or if you use BYO, the American cloud provider holds the key material. If they receive a Cloud Act warrant, they are legally obligated under U.S. law to decrypt the data and hand it over. But the exact millisecond they do that, they have engaged in an unauthorized data transfer to a foreign government under EU law, placing the customer in immediate massive breach of the GDPR. You are caught between two conflicting global superpowers.
And this is exactly why HYOK is moving from a paranoid edge case security measure to a mandatory architectural requirement for European
It's the
enterprises.
only way out.
Right. If you implement HYOK, the American cloud providers simply cannot comply with the U.S. warrant. They can hand over the ciphertext, but because the keys reside in your on-premise HSM in Germany, they cannot provide the plaintext. You have used cryptography to render the legal jurisdictional conflict completely irrelevant. HYOK is the only mathematically verifiable defense against extraterritorial legal overreach.
It is a massive game of international legal chess, and mathematics is the only winning move. You cannot rely on contracts. You must rely on verifiable technical controls.
Which provides a natural pivot to Section 4 of our deep dive, global regulatory compliance and frameworks.
The fun stuff for the auditors.
Oh, yeah. If you are an auditor, your entire professional life revolves around mapping these technical controls back to specific regulatory frameworks. Let's look at the frameworks highlighted in the research, starting with the evolution of the NIST cybersecurity framework, specifically the transition to NIST CSF 2.0.
The NIST CSF has been the global gold standard for cybersecurity blueprints for a decade. Historically, it operated on 5 core functions: identify, protect, detect, respond, and recover. It was a comprehensive, highly technical, risk-centric model.
But the 2.0 update changed the game.
It introduced a structural paradigm shift by adding a brand new 6th core function: govern.
And govern isn't just about technical IT configurations. It formally elevates cybersecurity from the server room to the boardroom.
Exactly. The govern function recognizes that you can have the best firewalls in the world, but if your organizational strategy is flawed, you will fail. It focuses heavily on executive accountability, continuous risk management strategies, and crucially, supply chain risk management. It dictates that the board of directors must have active visibility into the cyber risk posture.
So how do you actually track that across a multi-cloud environment?
From an architectural tooling perspective, tracking the govern function requires advanced cloud-native application protection platforms, or CNAPPs. The research highlights platforms like Prisma Cloud.
They use agentless scanning, right?
Yes. Agentless scanning means they connect directly to the cloud provider's APIs, rather than requiring you to install software on every single virtual machine. They ingest the metadata and immediately map your infrastructure's configuration state directly against the NIST CSF 2.0 framework. It gives the GOC analyst a real-time dashboard showing exactly where the architecture is failing to protect or govern requirements.
That level of continuous automated posture management is the only way to combat audit fatigue. You can't run these audits manually on spreadsheets anymore.
No, you'd never sleep.
Staying within the NIST ecosystem, the research also touches on the SP800 series publications. We have SP 800, 144, and 145, which provide the fundamental definitions and privacy guidelines for cloud computing. We have SP 800, 146, which analyzes the economics and elasticity of cloud models. But the heavyweight in this series that really dictates architecture is SP 800, 171, who is bound by 171.
Anyone doing business within the United States federal government supply chain. NIST SP 800, 171 dictates the strict security requirements for protecting controlled, unclassified information, or CUI, residing in non-federal systems.
So defense contractors.
If you are a defense contractor, an aerospace manufacturer, or a research university handling government grants, 171 is your mandate. It requires stringent controls around FIPS-validated encryption modules, strict multi-factor authentication, and continuous vulnerability scanning. Failing to map your cloud architecture to 800-171 doesn't just result in a fine, it means you immediately lose your Department of Defense contracts. It is a business-ending failure.
Okay, let's look across the pond at the international ISO standards. There is a frequent point of friction I hear from enterprise IT leaders. We just spent 9 months and $500,000 getting our organization ISO 27001 certified. Why is the GRC team now demanding we implement ISO 27017?
I hear that constantly.
What is the fundamental difference between the two?
It is a critical distinction in scope. ISO 27001 is a management system standard. It dictates the requirements for establishing, implementing, and maintaining an information security management system, an ISMS. It is the broad organizational framework that proves you have risk assessment processes and incident response plans in place.
Okay, and 27017?
ISO 27017, on the other hand, is not a standalone management system. It is code of practice. You cannot get certified in 27017 by itself. It acts as a cloud-specific plugin to your existing 27001 ISMS.
Why do we need a plugin?
Because the standard 27701 framework was written with traditional data centers in mind. It doesn't adequately address the unique, murky risks of cloud computing things, like hypervisor vulnerabilities, multi-tenant resource sharing, and the complexities of the shared responsibility model. ISO 27017 introduces specific controls designed to plug those cloud-native gaps.
Let's weave some of these specific controls into a real-world audit scenario. The research highlights 7 unique CLD controls introduced by 27017. Imagine an auditor walks into your organization to assess your multi-cloud environment. The first thing they're going to ask for is evidence of CLD.6.3.1. What are they looking for?
CLD.6.3.1 demands a documented, formalized shared responsibilities RACI matrix. RACI stands for Responsible, Accountable, Consulted, and Informed.
To clear up the blurry lines.
Exactly. The auditor wants to see a document that explicitly states exactly which party, your organization, or the cloud provider, is responsible for every single security layer. Who is responsible for patching the guest OS? Who is responsible for rotating the KMS keys? Who configures the WAF rules? If you have an incident and your engineering team points the finger at AWS and AWS points the finger at you, you fail the audit. The RCI matrix eliminates the ambiguity that leads to critical misconfigurations.
Okay, the auditor checks the RCI matrix. Next, they move to the lifecycle of the data and ask for evidence of CLD.8.1.5 removal of assets. How does an architect prove this?
This circles right back to our discussion on crypto shredding. The auditor wants verifiable proof that when a cloud service is terminated or a customer leaves, the data is entirely irrecoverable. Because you cannot show them a shredded physical hard drive, you must provide the automated SIEM logs proving that the specific KMS key encryption key associated with that tenant's data was permanently deleted, thereby verifying the cryptographic destruction of the data.
Moving to the compute layer, the auditor looks at how your engineering team deploys infrastructure and tests against CLD.9.5.2 VM hardening. In a cloud environment, developers are spinning up hundreds of EC2 instances or Azure VMs a day. How do you prove they are hardened?
You prove it through automated CI/CD pipelines and golden images. CLED 9.5.2 requires that you do not allow developers to manually spin up a raw operating system and configure it by hand.
So no rogue server setups?
None. You must utilize tools like HashiCorp Packard to build golden AMIs, Amazon Machine images. These images are pre-configured by the security team to align with strict CIS or NIST benchmarks. They have the necessary logging agents pre-installed, unnecessary ports closed, and default passwords disabled. The auditor wants to see that your IAM policies restrict developers to only launching virtual machines derived from these approved hardened golden images.
Finally, the auditor wants to see your continuous visibility capabilities aligning with CLD.12.4.5 cloud monitoring.
You cannot secure what you cannot see, and in the cloud, the control plane is everything. CLD.12.4.5 mandates the continuous ingestion and active alerting on cloud-specific control plane logs.
Not just application logs.
Right. We're not just talking about application error logs. We're talking about ingesting AWS CloudTrail, Azure Monitor, or Google Cloud Audit logs directly into your SIEM. The auditor wants to see your detection engineering. They want proof that if an unauthorized user attempts to alter an IAM policy, or if an administrator tries to export a massive dataset outside of a VPC perimeter, an automated alert fires to the Security Operations Center in near real time.
That continuous control plane monitoring is the only way to catch a breach before it becomes catastrophic.
Absolutely.
Now let's shift gears and examine the healthcare sector. We need to talk about HIPAA in the cloud. For an architect deploying healthcare workloads, the most critical operational hurdle is the BAA, the Business Associate Agreement.
The legal backbone of HIPAA in the cloud.
Yeah. For our listeners outside of healthcare, a BAA is a legally binding document where the cloud provider explicitly accepts liability for safeguarding protected health information, or PHI. It outlines the specific technical safeguards they will employ and their legal obligations regarding breach notification protocols. If you store a single byte of PHI in a cloud environment without a signed BAA in place, you are in immediate, massive violation of federal HIPAA regulations.
It's a huge deal.
But the research highlights a staggering operational difference in how the major cloud providers handle the activation of the BAA, and it's a trap that catches a lot of organizations.
It is a massive compliance trap. Most people assume that if a cloud provider advertises themselves as HIPAA compliant, you're safe out of the box. That is entirely false.
How does Azure handle it?
Microsoft Azure handles this with the least friction. For their enterprise customers, they generally apply the BAA automatically to their services globally.
Okay, what about AWS?
AWS requires a manual activation process. You must log into the AWS Artifact Console and manually accept and designate your account under the BAA before you store any PHI. If you architect a perfectly secure, encrypted, isolated environment, but you forget to click that acceptance button in the console, you are legally out of compliance.
Well, just a missed click.
Yep. And Google Cloud Platform is similar. They require you to submit a separate formal request through their Security and Compliance console to establish the BAA for your specific organization.
And beyond the activation, architects have to contend with service parity. Just because you signed a BAA with AWS does not mean you can use every single service in the AWS catalog to process PHI.
Exactly. The BAA only applies to specifically audited and eligible services.
Who's leading there?
AWS leads the industry here, boasting over 130 services that are HIPAA eligible. This is phenomenal if you are building complex, cutting-edge healthcare architectures that require advanced machine learning services like SageMaker for medical imaging analysis.
And Azure.
Azure has over 90 eligible services, but their true strength lies in their deep integration with the broader Microsoft healthcare ecosystem, easily bridging Office 365 compliance with Azure infrastructure.
GCP has a different angle, right?
GCP has over 80 covered services. While they have fewer total services covered, they shine in providing healthcare-specific APIs natively, like the Cloud Healthcare API. That includes default automated protections and de-identification tools that drastically minimize the risk of human configuration errors.
So as an architect, your reality is constantly cross-referencing your proposed architecture diagram with the provider's continually updating BAA-eligible services list. If a developer wants to use a brand new, highly efficient serverless tool, you have to block it until the provider officially brings it under the BAA umbrella.
It requires constant vigilance.
Which brings us to our final major topic of this deep dive, Section 5, data sovereignty, localization, and the absolute minefield of cross-border transfers.
This is where the lawyers and the architects really clash.
They do. Let's clear up a massive misconception right out of the gate, because I see architects and legal teams talking past each other on this constantly. We need to clearly define data residency versus data sovereignty. People use these terms interchangeably, but architecturally and legally they are entirely different concepts.
It is the most critical distinction in global cloud architecture.
Let's define them.
Data residency is purely a geographic fact. It answers the physical infrastructure question. Where does the hard drive storing the data sit? Have you configured your deployment so that the server rack is located in the Frankfurt region or the U.S. East Virginia region?
Right. And data sovereignty.
Data sovereignty, however, is a jurisdictional and legal concept. It answers the question, whose laws apply to the data stored on that hard drive?
So just because you achieve residency doesn't mean you achieve sovereignty.
Precisely. Let's say you are a French company storing French citizen data. You mandate that your engineering team only deploy resources in an AWS data center located physically in Paris. You have successfully achieved data residency in France.
Okay, seems secure.
However, because AWS is a United States headquartered corporation, the U.S. Cloud Act claims jurisdiction over the data controlled by that entity, regardless of its global location. Therefore, a foreign government still claims legal reach over your infrastructure. You have achieved residency, but you have not achieved data sovereignty.
And failing to understand that nuance relying solely on geographic residency while ignoring jurisdictional sovereignty can cost an organization dearly. Let's talk about the 1.2 billion euro lesson. The research details the monumental fine levied against Meta by the Irish Data Protection Commission under the GDPR.
A massive wake-up call for the industry.
Meta was transferring European user data from the EU to the United States for processing. To make this legally permissible, Meta was relying on standard contractual clauses, or SCCs. These are standard, legally binding templates approved by the EU, where the importing company promises to protect the data to GDPR standards. Meta had the lawyers sign the paperwork. So why did they get hit with a 1.2 billion euro fine if the contracts were in place?
Because the European Data Protection Board, following the fallout of the Schrems II ruling, determined that legal paperwork is entirely useless if it is not backed by verifiable technical controls.
So the paper wasn't enough?
No. Meta was using SCCs, but they were transferring the data to the U.S. in a way that left it technically exposed to U.S. national security surveillance programs, specifically under Section 702 of the FISA Act. The EU regulators essentially said, we don't care what promises you wrote in your contract. The U.S. government has the legal authority and the technical capability to intercept this data, so your contract is invalid.
The lesson for every GRC analyst and cloud architect listening is stark and undeniable. You cannot paper your way out of compliance anymore. Standard contractual clauses are considered insufficient supplementary safeguards on their own. If you are moving data across borders into a jurisdiction with conflicting surveillance laws, you must implement technical controls.
And by technical controls, we are circling right back to cryptography.
We are.
You must implement controls, like the strict HIPAA encryption architectures we discussed earlier, that mathematically prevent foreign governments from accessing the plaintext data, regardless of what subpoenas they issue or what contracts are signed. If the data is mathematically useless ciphertext, the transfer risk is mitigated. Technical enforcement is the new legal standard.
That is a massive paradigm shift. It elevates the cloud architect to the level of legal risk manager. Now, because of rulings like the Metafine, there is a lot of fear, uncertainty, and doubt surrounding EU cloud regulations. Let's dispel some of the myths based on the legal research we are reviewing. Myth number 1, European law mandates a strict data localization policy, meaning all servers must be physically located in the EU and US hyperscalers are essentially banned.
That is unequivocally false. There is no blanket general data localization requirement in European law that bans the use of US cloud providers. The GDPR is fundamentally a risk-based framework. It focuses on ensuring adequate safeguards, not drawing arbitrary geographic borders.
So you can still use AWS and Azure?
Yes. As we just discussed, if an organization implements rigorous, verifiable technical controls like robust access management, dynamic masking, and HYOK cryptography, they can absolutely leverage the scale and efficiency of US hyperscalers while remaining fully GDPR compliant.
However, while there isn't a blanket ban, the research points out that we are seeing the introduction of highly specific, sector-focused regulations that aggressively push the boundaries of operational sovereignty. For instance, we have the EU Data Act, which focuses heavily on preventing third-country governmental access to non-personal industrial data if that access conflicts with EU law. But the regulation that is really causing waves for architects is DORA, the Digital Operational Resilience Act.
Yes, DORA is a highly aggressive regulation laser-focused on the financial sector. It mandates extreme operational resilience for financial entities and, crucially, for their critical ICT, information and communication technology providers.
What does that mean for the hyperscalers?
Under DORA, if a major cloud provider like Azure or AWS is deemed critical to the stability of the European financial system, they are subjected to direct oversight by European regulatory authorities. Furthermore, DORA may require those critical ICT providers to establish a physical business presence and operational footprint within the EU.
So forcing them local.
It doesn't ban foreign tech, but it demands localized operational resilience. It ensures that if a geopolitical crisis occurs, the European financial system isn't entirely dependent on a control plane managed from Seattle.
We also have the European Commission's Cloud Sovereignty Framework. Now, this isn't a binding law, but rather a procurement guideline for EU institutions. It evaluates foreign influence and the reliance on non-EU technologies. It clearly signals that while there isn't a legal ban, the political and procurement winds are heavily favoring demonstrably sovereign solutions.
You have to prove sovereignty.
So let's bring this all together for the listener. You are an architect or a GRC analyst. You have data flowing across AWS and Azure. It's moving from the US to the EU. It's being processed by Spark jobs, ingested by AI models, and archived in immutable cold storage. You have dozens of IAM roles, hundreds of encryption keys, and thousands of compliance requirements. How on earth do you govern a multi-cloud, multi-jurisdictional web of this complexity without a team of 500 auditors?
You cannot do it manually. Relying on manual architecture reviews and spreadsheets is a guaranteed path to a breach. The research points emphatically to the necessity of implementing a unified metadata control plane. Platforms like Atlan are prime examples of this architectural necessity.
How does a metadata control plane actually function across disparate clouds?
Metadata is simply data about your data. A metadata control plane aggregates all the context surrounding every object in your environment. Where did this data originate? What is its compliance classification based on our Macy scans? Which ETL pipeline transformed it? What are the current IAM access entitlements associated with it?
It's a map of everything.
It's a live map. By maintaining active automated data lineage, these platforms can flag geographic and compliance risks in real time, often utilizing policy as code engines like Open Policy Agent or OPA.
Give me a real-time scenario.
Imagine a scenario where a developer accidentally misconfigures a Terraform script, creating an ETL pipeline that begins moving GDPR-protected PII from a secure bucket in Frankfurt to a US East processing cluster.
A massive violation.
Right. A metadata control plane detects that cross-border policy violation instantly It recognizes the classification tag of the data, evaluates the geographic destination of the API call, and blocks the transfer at the control plane level before the data ever leaves the region, long before an auditor would ever discover the violation in an annual review. It automates compliance enforcement and turns governance from a reactive scramble into a proactive, embedded architectural guardrail.
That is the ultimate goal. Security and compliance seamlessly embedded into the fabric of the deployment. Okay, let's unpack this entire deep dive and look toward the horizon. We have explored the strict requirements of data residency, the intricate complexities of the CDLM lifecycle, the friction of multi-cloud IAM, and the geopolitical battle surrounding cryptographic sovereignty.
We covered a ton of ground.
We did. But I want to leave you with a provocative thought to ponder as you architect your next environment. Everything we have discussed today relies on static infrastructure. We deploy a resource in a region, and it stays there.
For now, yes.
But we are rapidly moving into the era of agentic AI. We are not just talking about chatbots. We are talking about autonomous AI agents that actively execute highly complex operational tasks across your multi-cloud infrastructure.
That's coming faster than people think.
Imagine an AI agent programmed to optimize your multi-cloud compute costs in real time. The agent constantly monitors global pricing. It sees that GPU-spotted instances are currently 80% cheaper in an AWS region in Mumbai compared to your primary Azure region in Dublin.
Oh, I see where this is going.
So, acting completely autonomously, the AI spins up a compute cluster in India. It automatically migrates your massive data set across the globe. It processes the machine learning workload, returns the results to your dashboard in Europe, and destroys the temporary infrastructure in Mumbai, all in the span of an hour while you are sleeping.
It's brilliant for costs.
But terrible for compliance. How will our static, geographically bound data sovereignty laws adapt to an architecture where data is autonomously teleporting across international borders every few minutes to chase compute efficiency? Will the rise of agentic AI fundamentally break the very concept of geographic data residency? How do you write a standard contractual clause for an AI agent that changes its mind every 10 seconds?
You can't.
It is a fascinating collision of future automation and legacy law, and it is the exact challenge the architects of tomorrow are going to have to solve.
Thanks for tuning in to InfoSec Bytes. Keep exploring our 100-plus episodes on information security, AI, cloud, quantum, and cybersecurity, incident root cause analysis. Please like, subscribe. We are on various platforms, Spotify, Apple Podcasts, YouTube, Amazon Music, and share to stay connected and keep your cyber defenses strong. See you in the next episode. Stay tuned.